Okay, now I want to continue our discussion about traversing. This time I want to talk about the traverse computations, what it takes to do a traverse and actually go through the whole process, make an adjustment in the end, and then come up with your final result of what this traverse really ends up being. So let me just take you back. Our last videos that we had, we talked about closed traverses and open traverses. We talked about the benefits of one over the other. Closed traverse, of course, is the best, where you have control points, where you're starting on a control point, ending on a control point. That way you know exactly how well you did. And again, it could be geometrically closed or it could be geometrically open, whatever it may be. That's what we're going to be able to use to be able to know how well we did and to make any adjustments necessary. So again, here's an open traverse. We can see that we end up on something over here that we're just unsure of, is it right or wrong? It could be absolutely right, or there's a chance that it could have been some sort of error inside there that isn't good. All right, so in traverse computations, the thing what we're trying to do, it's an investigation of how well we did, of our precision. We want to figure out if we're going to either use the data we have or if we're going to reject it, if it was really good or not. We need to then figure out how to adjust the data. Now again, I'm not saying we're fixing the data or corrupting the data or changing it. No, we're making an adjustment of the data. Yes, the errors are in there. They're always going to be inside there. So there's no way we can get rid of them. But what we can do is adjust everything, whether it's evenly or proportionally, whatever it may be, to be able to say, all right, this is your final product. So to start, I just want to make sure that we have an understanding when we talk about rectangular coordinates. You've dealt with this from when you were a kid and when you were in algebra, figuring out timelines or figuring out anything you want to graph on a piece of paper. Everybody that loves to use their graphing calculators, you know exactly what we're talking about now when we have x and y coordinates. Okay, so now what we're going to talk about, and the thing we need to learn about, is if we're going from point to A or to B from point A, you have to start on A, and then we have to have what's called here a departure and also a latitude. Okay, and I'll define that here in just a sec. But what that's allowing us to do, if we want to get to point B from point A, well, you have to go so far in one direction, in cardinal directions in this case, you know, so far east or so far to the right and so far up and down, whatever it may be. So you take this, so here's a graph that we have. We have an x and y graph right here. What can also be considered to be an easting and a northing. So EastingNorthing meaning more along the ideas of for surveying, for design work, anything that you're dealing with the real world. You want to deal with everything in the proper orientation, the proper rotation. So you want to have, if it's east, if you're going to go to the right of your map here, then that's east. That's further east, further west, further south, and then further north. So that's why we call it eastings and northings, because they all have some sort of reference to how far you are north and how far you are east of another point. So departure then is this. If you're starting at A and you want to go to B, well, you want to know how far do we go to the east and then how far we go to the north. So departure then is how far you go to the east. So here's departure. And then here is latitude. Latitude makes sense, you know, as you're increasing in latitude, you're going either further north, or if you're decreasing in latitude, you're going further south. So it's an easy way to be able to remember that. So to come up with some fully adjusted computations, these are the steps that you're going to go through. You're going to first balance the angles. You're going to create your preliminary azimuths or bearings. You're going to calculate your departures and latitudes, calculate your linear misclosure, relative precision, then do your adjustment of your traverse, and in the end, you're then going to come up with your final azimuths or bearings and lengths based upon this whole adjustment. So for the first thing, what we're going to talk about then is how and what it means to balance our angles. So you take a look here. Here is a closed traverse. Here's geometrically closed, but also a traverse that's closed because we're starting at A, going to B to C to D to E and back to A. So A has known coordinate values, a known x and y, or a known northing and easting. So that means if I went all the way around, theoretically I should end up back at A precisely. So So the first thing you have to keep in mind that now at each control point or each traverse station, we make interior angles. We measure angles on the inside. So in doing so, we need to make sure, that's why previously we talked about, okay, if you have a polygon, how many angles what's the angular change that they're supposed to be? What's the angle supposed to sum up to be on the inside of there? And of course, on this case right here, you're going to be at n minus 2 times 180. Okay, so what that means is you can see that if I have my 5 angles inside here, here's my 5 angles, A through E. And you can see that I end up at 540 degrees, 0, 0, 11 seconds. So that means there's 11 seconds in there that I just didn't measure perfectly enough. That's just part of the air that's inside there. Okay, so what we have to do is then be able to balance those angles to make sure that this air, so we don't see the air basically. I wouldn't say it's a cover-up by any means, but it's a way of masking that air so long as it's small enough and acceptable enough. Previously in our previous lecture, we talked about what is acceptable, depending on what survey it is you want to do, whether it's a first order or a second order class 1, second order class 2, whatever it may be. If you fall within those standards and those limits, then you can go ahead and do an adjustment. So the first thing is balancing these angles. So there's 2 methods to balancing the angles. One is to apply an average correction to each angle, just meaning if I have 5 angles and I have 10 seconds of correction, or that I miss close by, well then every angle gets 2 seconds. Or you have what we call a customized correction. What that means is if you know at certain areas you did better than others. I measured these angles better because I could see better. I could see lower on the rod to really determine the precision of where the location of those locations are as you measure those angles. Then yes, you can apply your own personal corrections instead of an average correction. So the first one, let's take a look at just what the average correction is. This is what I'm telling you that, so if you look here, we had 11 seconds. 11 seconds that we missed close. So what that means is we have to correct every angle if we're doing an average correction. So we had 5 angles. So you take the 11 seconds divided by the 5 angles and you end up with a 2.2 second per angle correction. The correction obviously is the opposite of what your closure is. We missed close by 11 seconds, a positive 11 seconds. So our correction then needs to be a minus 2.2 seconds per angle. Now if you look at that, so now is where you have to kind of know what your rounding rules to make sure everything is legit and right. So we have to figure out that if you only had 11 seconds, we have to, obviously we can't put that evenly. Our instruments are only measuring to the nearest second, so we can only go to that. So what we're going to do is, one trick to do this is create a table of what the multiple of the average corrections are. So the first one is minus 2.2 at B. Right here you have minus 4.4, so twice the error, 3 times the error, 4 times, and 5 times the error. Okay, makes sense. That's just a simple thing to be able to do. Now take that and you're going to round. You're going to round each one of those. So what we have to figure out is that there's one additional second inside there that needs to get thrown in there somewhere and what angle it's going to be put at. This is where allows for the randomness of it, or where we're not trying to put it at one specific location. All right, so as you round those, then we're going to look at your successive differences. What that means is from 0 to minus 2. So you obviously we started at 0. So 0 to minus 2, you had a minus 2 seconds. Minus 2 to 4, and this is after the rounding, you had minus 2 seconds. 4 to 7, between here and here, you end up with minus 3. Here, 2, and then here, you had 2. So you can see now where that extra second gets thrown in there to make sure that those add up to 11. And that way when you make those corrections onto your angles, now that all adds up to be 540 degrees exact. So that's one method to be able to balance your angles, is taking that exact average, just showing you how to one simple way to be able to go through and make those the rounding portion to make it simpler, so it all ends up being even.